Hello everyone, it's Chemicator, welcome back to my channel. Today I wanna walk through the synthesis route and iconic properties of this peculiar structure. Cyclohexane or Janus Cyclohexane, synthesized by David O'Hagan in 2015 for the first time. And what makes stand out this molecule is that all 6 fluor atoms are cis together, which opens up a next level of synthetic materials. Why does this compound have such a significant importance? What features render it a beneficial molecule? What is the relationship between the thumbnail of the video and Janus Cyclohexane? And what can we do with this molecule? To answer these questions, we should zero in on the carbon-fluor bond, which is the unique bond in organic chemistry. So let's delve into it. CF bond is outstanding by virtue of high electronegativity and low polarizability of fluorine. It has the highest electronegativity of all the elements, rendering the carbon-fluorine bond highly polar, with a typical dipole moment of around 1.5 pi. But the fact is that perfluorocarbons like that of C6F14 are among the most non-polar solvents which stand in glaring opposition to the high polarized CF bond. How can you rationalize this apparent paradox? The reason is that all local dipole moments within the same molecule cancel out each other, leading in total to a non-polar compound. In semi-fluorinated compounds, some local dipole moments are not compensated, and the overall dipole moment is mirrored by its dielectric constant. The low polarizability and a slightly larger size of fluorine compared with hydrogen imply molecular dynamic of perfluorocompounds. Linear hydrocarbons have a linear zigzag conformation. In contrast, perfluorocarbons have a helical structure due to hysteric repulsion of fluorine substituents. Playing with molecules and manipulating them enables synthetic chemists to create new materials with groundbreaking functionalities. As you saw, linear perfluorocarbons are non-polar. Looking through the lens of a synthetic chemist, if you found a way that one free repulsion of fluorine atoms is maintained in the molecule, polar organic molecules would result. To this end, David O'Hagan group designed a cyclohexane skeleton that contains a fluorine atom on each carbon, in which all the fluorines are located on one face of the cyclohexane ring. Consequently, the other face is positive. This unique feature resembles the Janus, which is the god of duality in ancient Roman religion and myth. He is usually depicted as having 2 faces. Now let's go through the synthesis route. Myo-inositol was chosen as a starting material, which consists of 6 hydroxy substituents with cyclohexane core. Treatment with triethyl autoformate afforded the CH compound. In this way, 3 hydroxy groups were protected at the same time. Notice that ring flip is required for this reaction. In other words, 3 hydroxy groups attack to the autoformate when they are in the same plane, and this situation fulfills when 3 hydroxy groups are located in axial position. In the next step, the equatorial hydroxy group protected by benzyl chloride, and set the stage for protection of the axial hydroxy groups with hostile chloride. Then, this intermediate underwent selective deprotection, and exposure to hydrogen chloride opened up the cage intermediate. This process accompanied with ring flip to locate the bulky tosyl groups in equatorial position. Comparing to a starting material, these 4 steps were done to protect these 2 hydroxy groups and convert them into appropriate leaving group for the upcoming reaction. In the next step, exposure to the sodium methoxide triggers the intramolecular SN2 reaction. Mechanistically, the tosyl groups and adjacent hydroxy groups are below and below the plane respectively. So after deprotonation, the resulting enolates attack to the tosylate to afford diepoxide diol intermediate, in which hydroxy groups and epoxides are in the same plane. The high symmetry of this structure allowed the fluorines to be introduced in pairs over the next 2 steps. Treatment with Deoxofluor afforded the difluoro intermediate, in which the epoxides remained untouched. Furthermore, this process led to the inversion of two carbon atoms. Deoxofluor is a nucleophilic fluorinating reagent which converts alcohol to corresponding fluorinated compound. Mechanistically, hydroxy group first attacks to the S atom, and fluorine leaves the molecule. Now the hydroxy group is converted to a good leaving group since it is attached to the S atom. The attack of the fluoride ion on the carbon atom through the SN2 mechanism leads to the desired product, which is accompanied by an inversion of the stereochemistry of the carbon atom. In the next step, the epoxides were opened with triethylamine trihydrofluoride to a 4-tetrafluorodiol as a single isomer. The authors pointed out displacement of the hydroxy groups with fluorine should be completed sequentially rather than in a single transformation. To this end, this intermediate underwent monotrifylation. Then, exposure to triethylamine trihydrofluoride led to the substitution reaction. This process was repeated for the second hydroxy group to achieve the desired all-cis arrangement of the fluorine atoms around the ring. It's also worth mentioning that Frank Glorious in 2017 represented an incomparable groundbreaking synthesis of Janus Cyclohexane, in which hexafluorobenzene was converted to hexafluorocyclohexane just in one step. Frank Glorious group was working towards synthesizing fluorinated piperidines by the aromatization hydrogenation approach, which has paved the way for synthesizing Janus Cyclohexane. Glorious lab developed a rhodium carbon-based catalyst, which enables conversion of hexafluorobenzene to the unsaturated counterpart in one step and in a diastereoselective fashion. This approach is valuable not only for its one-step transformation, but also for the broad range of diversity it can bring. In other words, we can install different substituents on Janus Cyclohexane for different purposes. Thus, this approach equips chemists with an arsenal of fluorinated compounds.